Okay, is the screen visible to everybody? The my desktop.
Yes, sir.
Yes, sir.
Okay, so as usual, we will start with some of the queries that has been raised by some of you. Among them, what I feel is that one concept is needed to be just refreshed. So when we talk about partial orders, posets, then gradually we try to define these elements in the posets with respect to the Hasse diagram or a cover relationship diagram, which are maximal, minimal elements, what is greatest and least elements, what is upper and lower bounds, what is least upper bound and greatest lower bound. So to make it more clear, let us say that I have a set A of 1, 2, and 3. So if the poset is all possible subsets of A with respect to the subset equal relation, then I could find out this as my Hasse diagram. You have already seen in the slides and the lecture this thing. Now, if you look at this diagram, you can see that what is maximal element. So we say that each edge, this 2 is a cover for 5. Similarly, this 1, 3 is a cover for 1 as well as 1, 3 is a cover for 3. So this, whenever we draw an edge, we call this element as a cover for this, considering the relation subset equal. Now, the element for which no cover exists is or are the maximum elements. So there could be multiple maximum elements as well as minimal elements. That is one of the queries. So let us see these two things, it will be clear. So in this case, if I try to write the maximal element, as you can understand, it is 1, 2, 3. And the minimal element, if I write that for an element which is not covering any of them. So this minimum element here is the null set. In this case, in the right side of the diagram, what I made is that I made the poset of all proper subsets of it. That's why you see that 1, 2, 3 is not here. Now, if you look the same thing here, that what is the maximal elements, you can see that there are 3 elements for which no cover exists. So all these 3 elements are maximal elements. So that's the doubt, that there be multiple maximal elements and minimal elements. Yes, there can be. Now, if I consider that null set I will not consider in S, then there will be 3 minimal elements. Clear? Whoever has raised this question. In this case, the minimal elements is 1. Only 1, because I can find this one. Clear? Maximal, minimal elements doubt?
Sir, when we consider proper subset, why didn't we include 1, 2, 3?
Because I do not want to include the equal to. This proper subset is not equal to. All the subsets of A which are not equal to. This S contains all subsets of A which are not equal to A. Okay.
Yes.
Now look at the greatest and least elements. So greatest and least elements are a particular unique element if it exists. First of all, greatest and least elements may not exist as well. If it exists, it should be the unique element, that is an element from which every other elements are related by the relation, and that element doesn't have any cover for it. So that is the greatest element. Here, this is the greatest element. Here, this is the least element accordingly. Now, in this case, you will see that there are no such element where all other elements are related to it and it doesn't have a cover. Because see, this element, 1, 3 is not related to this one. If you consider 1, 3, 2, 3 is not related to this, 1, 2 is not related to this, right? So even 2 is not related to this. So therefore, in this case, there are many maximal elements, but there is no greatest element. However, this is the least element here also, because you can see that every element is covered by this and nobody is there whom this element covers. Therefore, this is the least element. Clear? Greatest and least elements.
So if we find multiple maximal elements, then
Yes.
we can say that there will be no greatest element.
If you find multiple maximal elements, there will be no, obviously, because the thing is that since you got multiple maximal elements, it may be the case that two elements are not related. Okay. So, I mean, the propositions here, somebody has, I mean, the doubt came that maximal and minimal elements can be unique or not. I mean, maximal, minimal elements can be multiple, but greatest and least element. So, maximal, minimal element must be present. That's one of the property, that max or mean element must be present. The second thing is that least or greatest element may not be present. But if it is present, if present, then there should be a unique least and greatest element. Okay?
Sir,
Yeah.
sir, in the first figure,
Mm-hmm.
sir, there is no connection between 1 and 1 to 3.
No, there is no connection between 1 and 1 to 3, but 1 is related to this is related to this. There is transitive relation of a poset makes your 1 is related to 1 to 3.
Okay. Okay, sir.
See, posets are transitive closure. So relation means not a direct path. Direct path is the cover, direct cover. Relation means if there exists a path through which you can reach from one element to other. Here you see there is no path to reach from 2 to 1, 3, right? Agreed?
Yes, sir. Yes, sir.
Good. Now just to complete, I mean, upper bounds and lower bounds, since we are calling maximal, minimal, all these elements over the whole poset. Now when we go for upper bounds and lower bound cases, what we do, we take a subset of it. I mean, let's say this particular subset, what is the upper bound and the lower bound of it? So you can see that upper bound or lower bound, this subset, you can see that this element is an upper bound. This element is also an upper bound, right? Because every element is related to them and they are covering each of the elements. I mean, I would say that no elements, I mean, every elements here are related to this one. And this is the element within this set, no one is related to, I mean, this is not covered by anyone. So this is an upper bound. Even outside this set, this element is also an upper bound of all these elements present in the set. Okay. So if you can if you agree with, there are two upper bounds here with the set that I have circled in white, then what is the least upper bound? This one, right? Right. So if I consider a subset, let's say I consider a subset T, which consists of elements 1, 2, and 1, 2, then of this T, the upper bounds will be 1, 2, which is obviously belongs to T. The upper bound is also 1, 2, 3, which doesn't belongs to T, but it belongs to the set S for which we are considering the whole poset. Now, among these two, this and this, the least upper bound is the element 1, 2, right? Because all other upper bounds, so 1, 2, 3 is a cover for this. If there are other upper bounds, if let's say for another example, you get other upper bounds, so this is related subset equal to relation to that other elements as well. So this is the, I would say the most succinct subset that you get out of all possible sets, all possible elements of this diagram. So this is the least upper bound. Similarly, we define the greatest upper bound as well, greatest lower bound as well. Clear? So just remember that least these bounds are with respect to a subset. We define these bounds. Okay.
Sir,
Mm-hmm.
sir, in the second poset S comma proper subset,
Mm-hmm.
so we define poset to be reflexive, right? So
Yes.
every number is subset of itself, not
Yes,
proper
yes.
subset.
So in Haschett diagram, we do not draw these edges. You are telling that these edges will be there, na?
Yes, sir.
We do not draw it in Haschett diagram. It is internally. These edges are internally there. Okay, we do not draw this.
But can we call it poset since the relation is not reflexive?
No, this which one?
Poset S comma proper subset. I'm speaking about that.
Okay, this one. No. So. Okay. Let us just not take this kind of a relation. I mean, what I want to show you is that I mean, let us take the same relation. Okay, let me do this one. Then let us take the same relation with all the proper subsets. So relation. I mistook in the relation. Relation is the same. Relation is this, but the set doesn't contain 1, 2, 3. This doesn't contain the element 1, 2, 3.
Also, sir, if we read poset power set of A comma subset, is it always trivial that we are taking the subset to A 1, 2, 3, or like previous we take reflexive all relation?
No, if you only consider, as you rightly pointed out, if you consider only this relation, this is not reflexive. So this relation is not a poset. That you are right. I have a mistake here. This relation with respect to any set, this relation will not be a poset because it is not reflexive.
Okay, sir.
Okay. Okay. So just to complete, since we are discussing all this, just to complete, lattice is basically whatever way you consider a subset, it must have a least upper bound and a greatest lower bound. Whatever way you consider, it must have a least upper bound and a greatest lower bound. Any possible subsets of this set must have a greatest lower bound and a least upper bound. That is a lattice. Okay. And that's why you can understand that upper bounds, again, like just like maximal, minimal elements, upper bounds could be multiple. Similarly, lower bounds could be multiple. But least upper bound and greatest lower bound could be unique. Right? Okay. Any questions in this part? This query? Anybody? So just to complete,
Sir,
yeah, please go ahead.
sir, if least upper bound does not exist, can we say that no upper bound exists?
I could not understand. Just come again.
Sir, my question is, if least upper bound does not exist, then can we conclude that no upper bound exists?
No, that if least upper bound doesn't exist, oh, yeah, the opposite way is obviously true. Definitely, because if there are some upper bounds, then there should be one least upper bound of it. Otherwise, no. This see here. No. I again misunderstood your question. You are saying that let's say this set there are two lower bounds. Okay, right, for this, and this is also a lower bound for this. Agreed? Yes or no?
Yes.
Let us consider this set. This will be easy for the upper bound case. So there are two upper bounds.
Yes, sir.
But is there any least upper bound?
No.
Yes. I hope that answers your question.
Yes.
So that's why this is a lattice. This one is a lattice, but this one is not a lattice. Agreed?
Yes, sir.
So can you again clarify the lattice definition?
So lattice definition is that any subset elements, if you choose any subset, must have a greatest lower bound and a least upper bound.
And how do we differentiate with respect to complete lattice?
How do you differentiate with respect to?
Complete lattice.
No, that definition is already given. I mean, just think of that definition once. I will then come. Just think of that definition. What is the definition? Tell me.
Yes, sir. I didn't get the difference between those definitions. In both you mentioned one. In one you mentioned
No,
it
one
contains.
I mentioned every pair of elements, right?
Yes, sir.
In complete, right? I mentioned every pair of elements. Yes or no?
Yes, sir.
And one I mentioned that lattice is complete if any subset of elements. Right? So this is a complete lattice. Because any subset of elements you get a least upper bound and greatest lower bound and least upper bound. And in lattice, what I mentioned is every pair xy. If you take every pair of element xy, then this must have a greatest upper bound and a least greatest lower bound and least upper bound. So this lattice is also a complete lattice. However, this is not a lattice at all, because you take every pair of element, you will not get a greatest lower bound and a least upper bound, right? See, every subset of element is a more strict condition, because every pair, if you take any pair, it is not every possible subset, right? Yes or no?
Yes, sir.
But every subset is more strict, right? Because if every subset has a greatest lower bound and a least upper bound, then obviously every pair has, because a pair is also a subset. But it may be the case that every pair has this condition, meaning that something is a lattice but not a complete lattice.
Sir, how is the first example you told the lattice, complete lattice?
Because you take any subset here, any subset of elements here, it has a least upper bound and a greatest lower bound.
Sir, how did you say
So,
that
see,
there may be upper bounds but not the least upper bound?
Consider this white.
So, sir, what is the upper bound here?
No, what I'm saying is that these are two maximal elements, right? See, again, upper bound. Upper bound definition is take a set. Okay. If an element is real, if all other elements are related to this is an upper bound, right?
Yes, sir.
So here, are there any upper bounds in this?
No, sir.
no.
So there is no question of least upper bound.
Yes, sir. Okay.
So if a poset has a greatest element and a least element, can we say that it will be a lattice, because these two cover everything, like the greatest and the least?
Yeah, these two covers everything. Yes, in that case, you may say that, yeah, if we have a least element and a greatest element, it just we need to think that if any possible examples is there.
Like the greatest element will cover everything, so every subset
Yeah,
is already covered by that, and we find upper bounds, and then we will take the list of them, and similarly for the lower bounds.
Least of the upper bounds might not exist.
that's what I am just thinking, that if always list of the upper bound may not exist. For every possible subset, it may not exist.
So give an example, please.
That's what I am thinking. Let me think of it. Just give me a minute. Let me think of it. Eddie, do you have any example in mind that greatest and least exist but not a lattice?
Like if we find nothing, then we just go to the greatest element. It covers everything. Then it itself will be the least upper bound if we find nothing else. And then we try to see if we have anything less than that.
Mm, I can find one. Let me check this one. Let's say you take the set of all divisors of a positive number. Okay, they are partially ordered by the divide relation. Yes or no? Every positive integer, take the set of divisors of positive integers. Right? Clearly, n. I mean, positive. If the positive integer was n, let's say 24. So 1 and 24 will be the least and the greatest element, right?
Yes, sir.
But now you take two prime divisors. Now that doesn't have any greatest lower bound or least upper bound.
So we take one as a lower bound. We have one in that set of divisors, and one divides everything. And the upper bound we multiply that prime. If we
Can
have
be
two
also.
primes, we obviously will have the product.
Okay, let me think a bit. I mean, I somehow can get an intuition, but will not create one. Let me think a bit. I will get back if at all exists. I believe there is two examples. I need to think a bit.
Also, sir, can you give one example for a lattice which is not complete?
Yeah. Lattice which is not complete. I can give an example. I'll tell you just. Let's say okay, lattice which is not complete. Let me go to the tutorial. I have one problem there. Okay, just wait a minute.
Okay.
I have a problem there in tutorial. Okay, any other questions? But your questions, I will think of it. I mean, I believe that there should be. I can create one. Let me see. Let me check if I am wrong. Otherwise, I will have to prove that no such thing exists.
So can we see it for the image that I have given?
Where you have given in the chat box.
Yes, sir.
Okay, let me just check the chat box once.
I've marked the set for which I did.
No, you see here the least upper bound is, you see that the top element is the least upper bound for this. The rightmost element you draw. No, the question is that, see, your rightmost element is the greatest and the leftmost element is the least, right? Now the question is that if there is a greatest and a least element, there is always a chance that we get a greatest lower bound and the least upper bound.
So, but for the set I have marked, there are 3 upper bounds, and for the smaller 2, we can't make a relation. I have marked a small subset.
Yes, you are right. See, check this example. I'm drawing it for all of you. Yes, you are right. I somehow messed it up. Yeah, check this example. Let me check it right. So here, what can be possible? I mean, what Gaurav has drawn is this one is correct example. Suppose I have this. Okay, so this is the maximum element and this is the minimum element, right? Now, by divisor, I also want to mean this one, but I cannot formalize in online right now. So let's say take these two elements. So these two elements C has an upper bound this one, has an upper bound this one, has an upper bound this one, right?
Yes, sir.
But you cannot say that which one is the least upper bound because these two elements are not related. These two elements are not related.
Okay, sir. Got
That's
it.
why I just want to mention, that's why I told that 1 and 6, let's say. Now you have 3 and 2, or maybe 2, I started with 24. So you have 3, 2 somewhere. Let's say 2 and 3 is this one. Now 2 and 3 may, I would say that there are two elements which are not related. Let's say 9 and 4 here. Okay. They should not be related to it, and maybe instead of 30, you say 36. So then you have a upper bound, but not a least upper bound.
So 9 and 4 cannot be the
Subset
point.
of 2. Anyway, I mean, I just want to point out that, I mean, where you get two different ways to go through the maximum elements, and they two are not related. Okay, so let's say this is 2 square into 3, and this is 2. No, in divisor it will not come anyway, because when you get a 2 with 3, then it's a problem. The 2 should be.
So, sir, this is not a lattice.
This is not a lattice. Definitely, every pair of elements there is no least upper. Okay, and if somebody has asked me about a lattice which is not complete, just wait a minute. I will show that not every pair of elements. I mean, you can think of this way, that let's say Q is a set of rational numbers. Okay. Q
Yes.
is or rather, I mean, in case of rational, let me otherwise all finite subsets. Okay, let's say all finite subsets of natural number with respect to union and intersection. I mean, union and intersection of finite subset is finite, right?
Yes, sir.
So if you take any of the operation as your order, I mean that should be a lattice, but the other one is not. Just wait a minute. I mean this rational thing I have it. I mean just let me do it there itself. Anyway, any other questions apart from the complete and not lattice but not complete? Then we can answer. Otherwise, we will proceed. Okay, this one I didn't understand the second question, to be very honest, because this one you have already answered, right? So see, I mean, obviously these two functions are from the set Z to Z. So obviously f is 1 to 1 because every element here, I mean, to have the condition 1 to 1 going, you know that if fx1 equal to fx2, obviously x1 equal to x2, because that's what fx1 tells. So this is 1 to 1. This is not because you have seen that we have +2 and -2, both maps to 4. So this is not. And gfx is not 1 to 1 because what is fx? Fx is x. Now, when you put a g of fx, you make x square. So g of fx is nothing but x square, which gives rise to the same thing. So it is not 1 to 1. I mean, do you have any other questions in your mind? Because you only wrote this much. I could not understand from it. I mean, what do you mean? Because this is the explanation. Okay, shall I proceed? Because this is nothing of a, I could not understand the question. Anyway, so this is, there is a question, this one, that we have defined projections. See, projections are nothing, you can visualize this. Let's say I am projecting a 2D element like this. What you do, suppose this is your x-axis, this is your y-axis, you have a xy coordinate. Now projection means that you project it into only x coordinate, that is this pi a, this relation, projection into first coordinate. So every element you project like this. This is the projection. So whatever elements you have here, you just project it and make it here. That's why I have pi AB to A, right? And similarly, the other direction projection is also the same because you project all the elements like this here in this direction. So that's why pi AB we put as a B. Okay. Now what I'm saying is that is C if it is a subset of A cross B, whatever A cross B can take, if it is a subset, then we define projection. But if it is equal to that, then both are onto functions because of the inclusion map, because everyone has an element here. So see, what does every element here say? So every element in this set has two coordinates, x1, y1, x2, y2. Now what I do, I project it into x1, I project it into x2, and I do so on. Now, if this contains every possible combinations, therefore for every x1, I have a corresponding x1 comma something here. For x2, I have a corresponding. So take any xi, there exists a xi y in this set. Suppose I call this set A and this, this set C. I'm projecting C to A. This set C and this set A. Now, for every xi belongs to A, I will get this kind of set in C because it's equal, such that this projection function is valid. Right? I mean, that's a trivial thing. That's why I do not prove it like this. That's a trivial thing. Yeah? So if it is equal, then only it's an onto function. So for every elements here, you will find some xy corresponding to it. And that will be within C because I have put the equal to relation. C contains every possible pay elements. Clear? Yes or no?
Yes, sir.
Okay, this.
Excuse me, sir.
Please.
Yes, sir, I have a query regarding the previous question which you explained, that x square and x1.
Mm-hmm.
So the condition was, I mean, in the slides you have told that if g of fx is 1, 1, then fx need to be 1, 1, and g of x should not. If g of x is 1, 1 or it is not, then it does not matter. So in this case, fx is 1, 1, but g of fx is not 1, 1, 1. Why so?
No. See, have you seen that if there is a composition, if this is 1 to 1, so what f should be and what g should be? If this is the case.
Means g should be 1 to 1 and f can be anything.
F need not matter, right? F could be anything.
Yes.
It should be 1 to 1. Now here though the opposite thing happens. Now how could you reason with the same thing? Here though this is not 1 to 1.
Okay, so I understood. Okay, sir.
So I took the reverse thing here. The theorem is the reverse, and you are going this way. If you have to go to reverse, then you see the reverse is a contrapositive. So G is not 1 to 1. F can be anything, implies FOG not 1 to 1. This happens here. Right? The contrapositive.
Okay,
what is the contrapositive? Contrapositive is G is not 1 to 1, implies FOG is also not 1 to 1. That happens now.
Okay.
Okay. This one is again the question is that there is a function a to b. We want to find the inverse image of a subset of b dash. So suppose there is a function a to b. So this is a and this is b. So somebody wants to find out. Let's say I have a subset which is b dash is a subset of b. Now, does f needs to be invertible? So if I want to find a subset image here, the pre-image of this subset, so is f needs to be invertible? What do you think, anybody? See, for one such subset I can find. For example, just take the example of fx equal to x square. Now, suppose my b dash contains of only one element 0. So I can have a pre-image here, and obviously I need to make the domain, let's say from Z to Z. I can have a pre-image here, right? It need not say that f should be invertible. One such subset can be found. I mean, one such subset can be found. That's not an issue. But the question is that if for all subsets I have a pre-image of them, then obviously that has to be invertible. Because otherwise, the all subsets means you said the subset is equal to also. The equal to case will otherwise contradict. Okay, understood. I mean, your question in a sense that if you want to find one such elements here which I can make a pre-image, yes, that could be one such element or some elements here. Yes, that could be possible even if f is not invertible. Here f is not invertible because since this thing is not bijective, therefore it could not be invertible. It's an if and only theorem, says if and only. Now, for all possible subsets, if it happens, then f must be invertible because all possible subset also contains b itself, subset or equality. Okay, is your doubt cleared? I mean, yes or no?
Sir, then also I think we can say that this function is onto but not invertible.
No, if for all subsets I have a pre-image.
Yes, sir.
So, for example, if this subset has a pre-image, it could have a pre-image only if it is one-to-one onto. Otherwise, how could the whole B could have a pre-image from it? No, in that case, you onto. How can you say onto? Because let's say this has a pre-image, but it doesn't mean that the whole thing should have a pre-image. How can you say f is onto?
No, you are saying that for all b dash we have a pre-image.
Yeah, I mean, I'm saying that if let's say if for all b dash is a subset of B, and you can find the inverse. It's not a pre-image. You see, find the inverse. You can find the inverse of. You can find f inverse of B. Then what is f? I mean, is f 1-to-1 or
Yes,
is
sir,
f
then.
1? Okay, think this one. Think this one.
Yes.
Sir, it might also be possible that we cannot find even one subset such that pre-image exists.
No. Yes, absolutely. It's the same thing. If I just eliminate 0, it will be the case now. If I just eliminate 0, you will not find in the same example. Absolutely. No, I am saying that there is a possibility that one such thing happens, still it is not invertible. It could be a possibility, but you are right. I just eliminate 0, all the non-zero roots, all the non-zero squares. You will not find this.
Okay.
Okay.
Actually, this question is not very clear to me.
Exactly. I'm also not very clear. I just gave some of the alternatives. That's
F inverse B prime is defined as a subset of A. It may be empty.
It may be empty as well. Exactly.
So, what is the query really? No question of invertibility onto-ness or on.
Exactly. We cannot tell anything about f with this.
Yeah, F inverse B prime is defined as a subset of A. That's all.
Just a subset. Okay. Anyway, I mean, if whoever questioned it, can you make it clear? Otherwise, we will move on. Okay. Yeah. Now these are the questions from Stirling numbers. So there is a question says that suppose I have a m cross n matrix, assuming m greater than equal to n, you have a 2D array of m rows, 0, 1, m minus 1, and 0, 1, n columns, n minus 1. Obviously, m greater than n, number of rows are more. So it is said that the entries could be 0 and 1 with exactly 1 in every row. So I can place a 1 here, I can place 1 here, 1 here, like that, 1 in every row, but at least 1 in every column. So in every column here I can place a 1. Okay. Somewhere here I can place a 1. At least 1 in every column. Now, somebody told, I mean, it is there in the slide that this is also a, how many number of such arrays can be found, such two-dimensional arrays can be initialized like this, is the count of onto functions. So somebody says how it is related to it. Just take the theoretic way. Suppose you have m elements here, and you have n elements here. Now see that each of this m, for each of the n elements marked as 0, 1, up to n minus 1, each of them, if, see, this element is from this row, and this one of the same column is from this row. Suppose this is I and this is j. So I have I and I have j, and there is something k where I map into. Agreed? Yes or no?
Yes, sir.
Now see, at least 1 in every column. So every column should have at least one pre-image from him. So this makes this function as onto functions, because at least 1 in every column is there. So every column must be attached to some row at least once, maybe more, but at least one. So it makes it as an onto function. And the way, since one column can be multiple row, can be making that column as one. So there could be multiple edges also possible. So how many onto functions is the number of ways you initialize. Did you get the relation now?
Sir, what is that exactly one?
What is that? Oh, exactly
That
one means
exactly
each, no, this each row is that, otherwise it will not be a function. Na? If each row, see, each row means what? This. Exactly, there is one edge going here. It could not be the case that two edge goes out here to two different places. Each row has exactly one once. That means each row maps to exactly one element here. Each row, when each entry in this set A exactly match to one entry in B. If that is not the case, then this will not be a function at all, isn't it? Suppose an element in A maps to two different elements. It's a relation. It's not a function. Agreed?
Okay, sir. Yes, sir.
So that's why each row one is enforcing the function definition, and at least one it enforcing the onto definition. Get it? So it's the number of onto functions now you have to count, because the placement of A will dictate these edges, different ways you can make the onto function. Okay.
Yes, sir.
Okay. Now this question actually I do not have an answer, because see, these questions are different. So you said that, is there any relation between Starling number and the number of possible combinations of this? I mean, this x1 to xn equal to m, how many solutions we have, right? When xi equal to 0. So because see, what does an onto function justify? Suppose I have an a to b, this function is onto. It justifies that all elements here must have a pre-image in this set, right? All elements here. But there could be some elements here remained also. That I don't care. I could have only this much element to map all of them. Only this much elements mapped all of them. There are some elements still left. Right? This is the definition of onto function. Yes or no? Agreed, right? Now look at this relation. What do we do in this? X1 plus x2 plus xn equal to m. We try to place this m number of balls into this. Now suppose these are my balls, and these are m number of balls, and these are my basket. So if you, even if you try to consider that, see, each basket, as you said, greater than equal to 0, make sure that each one, here is the ball coming here. This ball may also come here. I can understand that, but here you have to exhaust this M set, wherein a number of onto functions you may not. Do you get it?
Sir, how can we not say that there will be some elements in A which are not mapped to B? Because function, if we define A as domain, then it must be defined for all elements in A.
No, but see, so is it? I mean, this may not be the case. I mean, all elements, the onto function is all elements here should have a pre-image here. It may not span across everything.
But sir, each element in A must have a connection to B. Otherwise, how will means then for the remaining elements FA will not be defined. Then how is it in the domain?
No, see, domain. That's why. Let me open the slide. Domain is a different thing that we. Let me open the slide. I will explain you this. Just give me a minute. I have drawn a figure in the slide. If you could see here. So, what is exactly your question there? I mean, you were saying that every element of A should be there, right?
Yes, means all elements in A must have an image if A is the domain.
Okay, so if you guarantee that, we have not thought in this way that whether these two will be equal or number of onto functions. Where we miss, let us think.
Sir, the remaining one will also map to the B. Like the function will not one to one.
No, it's not about one to one. It's a onto function. See, I mean, what his query is that these are balls, okay, and these are baskets. Now his query is that, see, I have n baskets, that is perfect. I have m balls, and he makes sure that at least one ball goes into every basket. So therefore, since he makes sure that at least one ball goes into every basket, so no basket will be empty. So there should be incoming edge to every element here. Now he says that the number of onto functions from this set to this set is equal to the number of counts that may happen to solve this equation.
Sir, but the balls are not means they are not similar. They are distinct.
So for Stirling numbers, we assume that all identical boxes are there, but in this, the images of x can be different. So into
So
n
here,
factorial,
let's say the balls are numbered x1 and x2, right?
Yes, sir. Then it will be the same. But
Yeah.
then that won't be the Stirling number. It will be n factorial times that Stirling number.
Exactly.
That will be the number of functions.
Exactly. But the thing is that here we label the elements, and here, so in finding the number of onto functions, in case of elements, we label it as x1, x2, and x1 goes to this basket, x2 goes to this basket, and so on. But here, when you go putting the balls into x1, these m's all are identical, right, Gaurav? Otherwise, if you make it that ball x1, x2 are not identical, it's labeled, then it's the same.
Yes, sir, understood. Balls are numbered here.
Yeah, balls are numbered.
Sir.
Yes.
Sir, in the query which you have written that how the problem of finding total number of 2D matrix with entries only 0, 1 having exactly 1 in every row and 1, 1 in every column. So, sir, how can it be possible
at
that...
least, at least.
Okay, sorry, I thought it is exact, sorry.
No, at least. Exact hone se this is wrong. This exact thing is, if it is exact, then that is not a all possible onto function.
Yes.
Right. If it is exact one, how it could not be all possible onto functions. And if it is exact one, the problem will be if m is greater than equal to n, you cannot do it. Na? If m is greater than n.
Yes.
So here can we say that the number of onto functions is equal to like mcx1 into m minus x1 cx2 into m minus x1 plus x2 cx3, like this going on.
No, actually the relation is given. Na? It's this one. When you compute everything, then you have to give a combinations of this m minus 1, n minus 8, and then plus 8 and so on.
So I'm speaking in terms of x1 and these things, x1, x2, xn. Means suppose x1, suppose all these values are given to us, means for a certain combination.
I mean, you are saying that let's say 1 plus 2 plus 3 equal to 6, like that. Then?
Yes.
Then
Then
what
it will be like mc1 into mc, no, m minus 1 c2 into m minus 3 c3.
No. This problem, even if the balls are identical, this problem is not solved by this way. I mean, this is other thing. See, if the balls are identical, you understand. I have to differentiate it within m minus 1 once because there are m gaps. Then, sorry, I have to differentiate with n minus 1 once. So there are n baskets. Then I place the balls like this with zeros. Right.
Yes,
so now if what you want to do it as mc1 this way.
Yes.
Plus.
And then not plus into m minus 1 c2.
No, what is your aim in that in m minus 1 c2? Let me write it in this way. I mean, what is the meaning of this? I mean,
one ball is taken, then m minus 1 are left.
So 2 by 2, 1, 2. Why this is 1? Why this is 2?
Means the first one, x1 is 1. Means
No. Then so you already are you have to explore every possible combination. You have to explore 1 plus 1 plus 4.
Yeah.
You have to explore 2 plus 1 plus 3. So then to ho hi gaya na. These are the number of solutions.
Yes, sir.
So number of additions he will go and make, and this is the number of solutions. No, this will make complicate things. The analogy of using this binary number is the most easy to comprehend in this case. Okay, so just let us take a minute or two break, and then we can start the tutorial. But before you go to break, just let me give you one announcement here. We have to make that next week we have a test number 1, so which is basically the week of the date is 5th October, Tuesday, right? So the same time, in the same format, we will do. I will drop a mail. The syllabus is up to whatever is covered today. That means up to set function relations, whatever being covered. Okay. So same time, same type of test we will give. The instructions we will tell you, and it will be in the similar manner as you have done in the first test. Okay.
Sir, will the syllabus will contain the previously covered topics like before test 1?
Eddie, what should we do?
All previously covered topics must be there because you are asked to prove something.
Exactly.
You have to use proof techniques.
And suppose we write for all, is it not in the syllabus?
Yeah, so it's still implicitly there.
Yes.
So without knowing proof techniques, you cannot prove anything.
Okay, so any other questions?
So is it possible to take the solution on Moodle because the Google form doesn't allow multiple PDFs to submit? Previous time.
No. So this time what we will try to do is that you complete everything. The last 10 minutes you go on submitting. When you complete, you submit. The exam will be of 1 hour. Submission will be of 15 minutes. Let us make it crystal clear. You do it whatever you can do in an hour, and then you submit.
Only one submission.
Only one submission. Just like you submit your answer script and leave out of your room if it is a live exam. Okay, that we will do 1 hour. Then we'll say exam stop. Then you submit whenever you.
Sir, in the last query you discussed.
Your voice isn't clear. Can you repeat?
Sir, in the last query you have discussed.
In the last query
that you have discussed.
Device disconnected.
Just Eddie, could you make what he said in the last? I could not make out.
No, I also didn't.
Sir, in the previous slide, am I audible now?
Okay, you are talking about this. Okay, in the previous slide, yes.
Yes, sir. Here we cannot say that the total number of onto functions can be m factorial into the possible ways of x1 plus x2 and so on equal to m, right?
No, that we are not saying that. I mean, we can only say it if your m's are labeled, because in functions we label x1 and then map it to somewhere here. For identical m's, we are not saying these two will give the same result.
Okay.
Okay. So, any other questions about the our test?
Sir, sir, is predicate and propositional logic also there?
What Eddie already said you, yeah. Come on. If we have to write something like that, if you do not know what is for all, you said it is not out of syllabus, then how can we do that, right? How can you eliminate group techniques? Suppose you say that 11, 12 ho gaya, induction we will not use. You cannot do that. Okay. The second announcement is that we will upload 3 hours of lecture this week. But due to the next week is your exam week, we will not have any tutorial before DP. So next week we are just leaving it. After that week is a DP week. We have a holiday. So then when we come back, we will have a tutorial for this lecture set that we upload. And we will proceed accordingly again. Okay. Okay. So just let me pose the first question, and if you want to take a 2 minutes break, you go ahead, and if you want to solve, you solve. And I will just start after 2-3 minutes. Okay, let us start. How about this one? This says that you have a function small f from a to b and a capital F function from power set of a to power set of b such that f of s is equal to small f of s. By just one thing here I would like to clarify more is that by this set I want to mean it's a set all elements such that fs is equal to t where s belongs to a. Okay, so this I mean it's obviously a subset of b.
So small s belongs to A or capital S?
Sorry, this is capital S. Obviously belongs to A because S is a subset of A. S is a subset equal to A. But to be more precise. Okay, so A. Let us consider this direction first. How do you go? That means if F is injective, you need to prove capital F is also injective. This is a simple problem. I think everyone can do it. What does the definition of injective says? It says that if FA1 is equal to FA2, it implies A1 equal to A2. That's the definition of injective. Right? Now, due to this definition, can we extend the same thing by telling that for all A1s which are inside S1, for all A2s which are inside the set S2, can this be written? Yes or no? Because it happens for any pair of A1, A2. Now see, this relation automatically says this is nothing but Fs1 and this is nothing but Fs2. So this automatically says capital F function is also injective, right? It says that capital F is injective.
Sir, the capital F function is defined from power set of A to power set of B.
Yes, yes, yes.
And sir, still like we are defining only Fs equals to Fs for all S which is subset of A. So sir, there are a lot of elements of capital F that are not defined.
For all subsets of A, this holds. For all subsets of A, this holds.
Yes, sir. And for other elements of power set of A, what is the value of F?
No, I couldn't understand one thing. That see, this function is from two power sets. That is the sets of elements from A to the sets of elements from B. For all other elements, meaning?
So like power set of A has all the subsets of A also, no?
Yes. So this is a function which defines that. Na? So suppose A is 1, 2, 3. So I have power set of A as these elements. Na?
Yes, sir. So what is capital F of 1, 2?
Yes, that is power set of B something. Suppose power set of B is ABC. Maybe 1, 2 maps into A, 1. Suppose B set is ABC and A set is 1, 2, 3.
So this means like what it can be anything. We are only defining for S that is subset of A.
Yes, I mean, see this. So since this relation is given, it means that A and B, so A is 1, 2, and 3, and B you have A, B, and C. So for 1 and 2, if you take the set of 1 and 2 in A, you will get A and B here. That's what we are saying by this equality. This is A, this is B, this is your F function. So if you take 1 and 2, you will get A and B, this set here. This Fs, where here your S is this one, or subset of A is 1, 2, let's say. That this is one example that I give. What is your question now?
Yes, sir. Thank you.
Okay, so similarly, you go for this way. If F is injective, definition is two sets of S1, S2 imply these two sets are equal. This is given. Now you have to prove that F is injective. The same way, right? The reverse direction we can do. So this is nothing but it says that Fs1 is equal to Fs2 implies S1 is equal to S2. And you can analyze that since these two maps into the same set, then for every elements of this one, some elements of this one will map to the same place. So therefore, every pair of there could be two elements AI equal to AJ. I mean, I would say FAI equal to FAJ. That will imply AI equal to AJ as well, meaning that F is injective. This is just a warm-up problem. I mean, you can just, if you visualize, you can see that every direction it is happening. Okay, surjective one. Can you come up with the surjective one? This side, let's say. What is the definition of surjective? F is surjective. When F is subjective? Suppose for any B belongs to B, you get there exists an A belongs to A such that FA is equal to B. That is the definition of F is surjective, which is given in our case. Okay. It easily followed, right? Because any B, if you cluster some of the B's, from there, it will be some set T, which is a subset of B. For those sets of B, we have the corresponding A's here also, right? You have the corresponding A's here also. There will be some A's such that since the relation holds for Fs equal to small fs, right? So any subset if you take, those elements have a pre-image here due to F is surjective. So that subset would have a pre-image subset here such that this relation. So capital F is also surjective. Okay.
Sir? Sir, can we say that this capital F and small f, these two functions are equal?
No, these two functions are not equal. See, these are defined over different domains and codomains. How can you say these are equal?
Okay, sir.
So small f takes elements like this and maps into something. Capital F takes a set like this and maps into a set like this. How can these two functions be equal? Right?
Okay, sir.
So bijective is just this. If you can prove this two, this is just a follow-up of this. Okay, I am not doing this side. This side you do. This is just a warm-up. Okay, everybody?
So I have a doubt regarding the equal functions. So let's say I have two functions, fx equal to x square and gx equal to x square. Okay. But f is from R to R and g is from R to C.
Wait. Let me write it. Okay. If you said that fx
is x square.
Is x square and gx is
x square.
Okay, and f is the domain is from
R to R.
R to R.
And G is from R to C.
R to C, where C is your complex number.
Yeah. Yeah.
Okay.
So these are not equal, right?
I mean, not equal in the sense. I mean, what you want to?
The codomains are different. One is R and one is C. So these functions are not equal. So,
yeah, I mean, if you take a subset of this codomain, it is just the R, right? Because you do not have the complex part here.
Yeah, but I mean, from the definition we get that these are different.
Yeah, from the definition you can say these are different because these are defined over different domains.
So what does this imply? Like, we have these functions which give same values for all values in the domain, but just the codomains are different.
Yeah,
we have the same range as well.
Yeah,
so
this implies that if you take a projection of G function onto real coordinates, then this will be the same.
Okay.
If you take a projection, this will be the same. Otherwise, it's not the same. Usually, I mean, see, usually we do not I mean, in practical applications, we do not. I mean, the example you have given is a pathological example because in practical application, usually we say a function is same or different when this is not different. But here itself is a difference.
I mean, the codomain does not matter that much because ultimately it boils down to the range.
No. Why it matters, you know, intuitively, it transforms this number here into a altogether different plane, right? It's an Argand plane you have transferred into.
But all the points lie in that real line only. Nothing goes outside that real line.
True, but this domain is a different domain altogether from this. So why I am saying this one? See, this have now a R theta something, right? Whereas it's totally in real number. It's not in Argand plane, so you cannot have any R theta. So the I would say the treatment of this now after you translate into C domain, it's totally different. So that's why now if you have to compose G with something, you say that I will compose F with something and get back the same result. May not be the case. You may have to compose with the arguments and all these things, and R theta, all these things.
Okay,
that's
so
why
we take that Gx as a complex number.
Exactly, because you said that the Gx will map into the complex domain.
Okay, it's just the different treatment. The values are still the same. The values will be equal, but we treat them differently.
See, values will be equal because you are thinking that the real and the complex plane falls in the same real line for the real part. That if I say that these two are totally different domains, then it's not the same. We are not in the same place.
That's why we define the complex plane like that. Like R is a subset of C.
Yes, that's right. Okay, but usually when we say equal function or not, now we assume that this is equal and we differentiate here. Your case is a pathological case, but since the definition says us these two treatments are different, where do you map and project into? Therefore, it should be different. Fx Gx could not be treated similarly, so they are different, not equal.
Okay.
So if G goes from R to R plus, then we can say that G is onto but F is not. So that will create one difference.
If R to R plus, yeah, I mean that you can say it's onto and not.
We can we actually do R to R plus? We have to include 0.
Yeah, I mean, let's say he includes 0 also. Let's say R0 and plus. Let's say only positive real numbers. R2 only positive real numbers, including 0. Yes. Okay, but definition wise, these two will be the different.
Okay.
This one. A little non-trivial, not this part, the next part that I will show. First 3 parts are very easy. You can just open your notebook and start doing. A to B is a function. Sigma is an equivalence relation. This is an equivalence relation given. I define a relation rho such that A rho A dash, both A and A dash are from A, if and only if this happens. Fa sigma Fa. Okay. A is from A, Fa is from B. That you can understand. Now you have to prove rho is an equivalence relation. So first let us tackle only the A problem. So what is the conditions of equivalence relation you have to show? Try to show it is reflexive, symmetric, and transitive. Reflexive, what you will do? Can you show this happens? Is this true? A rho A? Can A rho A be related to A itself?
Yes, sir.
Yes, because Fa is related to Fa itself due to this being an equivalence relation given. Right? This if and only if Fa. So this if and only if Fa. So this holds. Symmetric. If A rho A dash, I have given if and only if Fa sigma Fa dash. Now, sigma is equivalence relation, meaning this imply Fa dash sigma Fa, because equivalence relations are symmetric. Yes or no? This means if and only this. So starting from here, I can say this. Agreed?
Yes, sir. So can you repeat this?
See, look at this one. I mean, let me highlight this. This green part is very important for us, and this yellow part is very important for us. So A rho A dash. I have to from here. I have to go implying this. Then only I can prove that these are symmetric. Right? Then only I can prove rho is symmetric. Now A rho A dash, if and only if Fa sigma Fa dash given by the relation definition. Now Fa sigma A dash, since sigma is a symmetric relation because it's equivalent, symmetry property should hold. So Fa dash sigma Fa will imply Fa dash sigma Fa. Now this if and only if this, because it is the definition of the rho relation. Okay, so from here I get an implication to here. Clear?
Okay.
Transitive you do. I will not do for you. You do this. This should imply you do it yourself. Similar nature. From here I get here. From this I get something. Those two with sigma are transitive. They will give a transitive relation with A dash and A double dash and A. That will give rise to this one. Okay, can you visualize now?
Yes, sir.
Second one. I define an additional map, which is, see, the equivalence classes of A, since rho is now an equivalence relation we have proven, the equivalence classes of A with respect to the relation rho and the equivalence classes of B with respect to the relation sigma. Both are equivalent relations, so they will define certain equivalence classes. And this is the map. So a class here maps to like this. We denote it this way. Now prove that this is well defined. By the definition well defined, so a function f is well defined when if you take two elements a1 and a2, if you take two elements a1 and a2 and if they are different, then it will imply that if a1 or the other way, sorry, if let's say if I take two elements, if they are same, it will imply f a1 equal to f a2. That is well defined. So two elements give rise to the same. The definition of the function that by which we define a function. Okay, so here can you prove this now? So what
means
you
they
have
are 1 to 1.
No. 1 to 1 is the reverse. 1 to 1 is the reverse. Do not confuse this. 1 to 1 is the reverse, na?
Yes, sir.
So this one, we have to prove what if this one happens, meaning, so why this is important, you know, why it is important to prove equivalence, I mean the well-definedness, because A1 and A2 may be two different elements belonging to same class. Right? A1 and A2 may be two different elements belonging to same class. Yes or no?
Yes, sir.
But you see, let me give you a function where it doesn't hold. Why it is easy to prove. Suppose I have this modulo 5 and I go to modulo 6. I have this function. Now, therefore, each element with this has a map with this equivalence class. Now consider these two elements. Suppose 0 with 5 is equal to 5 modulo 5. But 0, 6 is not equal to 5 into 6. Right? So I have a map here. So, right? So this is not well defined. But in our case, since we have a certain relation like this one, if and only if arrow A, this will be well defined. So we have to prove that if this is the case, we need to prove if this is the case, then f A1 class with respect to sigma is same as the f A2 class with respect to sigma. That means FA1 and FA2 belongs to same class in sigma with respect to sigma. Okay, with this definitions and all that, it is easy right now from here to go. Yes or no? See, this what does this equal to relation immediately translate into? This equal to relation will translate into, what does this equal to relation will translate into? If this is equal, I need to prove A1 row is equal to F A2 row. Right? Now look at this map. So this says that F A1 sigma is equal to F A2 sigma. This is the map. A row class maps to FA sigma class. So A row class maps to FA sigma class. A row class maps to FA sigma class. Okay. Yes or no?
Yes.
See injectiveness. F bar, this function is injective. You know how to prove injective, right? I have to prove that F A1 sigma equal to given F A2 sigma. Then I have to prove this will imply A1 row is equal to A2 row. I have to prove this one, prove this. So what does this came from? This is basically nothing, but when I have F, I apply F bar function here, I reach here. So this is nothing, sorry, this one be false. Yeah. This is nothing, this is F bar A1 row is equal to F bar A2 row. F bar A2 row. This is F bar A2. Okay, just the definition because of this map. Yes or no? Agreed though?
Yes, sir.
Now what you will say? The next thing. See, now the fact is I have a relation that FA1 sigma FA2 if and only if A rho A1 rho A2. This is given to me. Agreed? So if these two are related, therefore the class that A1 belongs is also related to the class A2 belongs. And if these two are related, the class that FA1 belongs with respect to sigma is also equal to the class FA2 belongs with respect to sigma. Doesn't it imply this one then? Okay. Yes or no?
Yes, sir.
See, if two elements are related, both of them, the class will be the same where they belong. So here, this one. Again, here two of them are related, so the class they belong will be the same with respect to the equivalence relation sigma. So these two are whatever. From this one, I want to prove this one. If and only if this, I have a relation. So this is injecting automatically. 1 to 1. Okay.
So,
yeah.
Sir, in proving the second part, we took A1 row equal to A2 row. I mean, class A1 row equal to class A2 row, right? We started with.
No. We started, that's why I put an arrow here. We started with this one. We started with this.
No, sir, in part B.
In part B. Yeah. Yeah.
Then without knowing that F bar is well defined, how can we write that F of A1 row equal to F bar of A2 row?
No. See, A1 row, if these two elements are equal, no, I am not saying I will write it here. What I said is that, see, that it means in the same relation, it means A1 row A2, right?
Yes.
If and only if A1 sigma FA2, right?
Yes, sir.
Now, if this happens, then this will also happen, this part. Agreed?
From the definition of
the classes are the same. FA1 is related to FA2 with respect to relation sigma. So the classes will be the same. These are the class. This is just the set of the elements. The classes will be the same. And due to the definitions of equivalence partition, you will have disjoint sets and every elements are related within a set. Right?
Yes.
And then from here I reach here. No, when I put an arrow here, I mean, from here, how can I prove this one? Then I say you try to prove this one, this will reach here. And from this definition, automatically these two are equivalent. Okay?
Yes.
Okay. These two are a little bit tricky. Try to think. So we have proven that F bar is a injection already. So if F is a bijection, then so also F bar. So only thing needs to be proven is that F bar is surjective, because I do not care the bijection part to prove F bar is injective. I automatically proved it. So you need to only prove F is surjective. To prove this one, test prove, you have to take an example. First of all, just think that whether the first one can be proven or disproven. Whether D is correct statement or false. The statement of D is proven or not, true or false?
Sir, it seems to be true, sir.
Okay. So you need to only prove the surjective part. Yes, you are right. So for the surjective part, what we need to prove? To prove F bar to be Surjective. So take any B, any class here. Take any class. We are proving F bar surjective. So this codomain is a set of equivalence classes. So take any class which belongs to here, right? Since F is a bijection, so F is surjective as well, given. F is a bijection, it is given. So F is surjective as well. So therefore, for any B, we have a corresponding A such that this holds. Okay. Now try to look at what does this mean. This is nothing but F of A sigma. Since B is equal to FA, this is B sigma, right? So it implies that some B has a pre-image. So this as a pre-image, there exists a row such that we have this. So F bar is also surjective. Okay. Yes or no?
Yes, sir.
See, just you visualize what is your F. Your F is from an element to an element. So F, there are elements here. From an element to an element is your F. This is your F function. What is your B? B function is basically you put down in, what is your F bar? F bar function is basically you put down into equivalence classes. From the elements in A, you have cluster a set of elements into equivalent classes here. And then from here, this side also you have clustered into some equivalence classes. Here also some set got clustered into equivalence classes. Now I define mapping this like this. Now I prove the bijection of F bar as well. Okay, that's what we proved here. So E, what do you think? The opposite. If F bar is a bijection, then F is also a bijection.
Sir, it is false, sir.
Counter example.
Sir, the function from natural numbers to the set 0, 1, where we take the modulo 2.
F is, you are saying F is a function from natural number to 0. This side is closed?
0, 1.
This side closed or open?
No,
open.
Sir, only 0 and only 1. 2 elements.
Okay, 2 elements. Okay. 2 elements. Let us say 0, 1.
And we take the remainder when.
So the relation rho you are saying is relation rho is x modulo 2, right?
Yes, sir.
And what is F bar? So obviously this is not a bijection because F is since there is 0, 1, you map multiple elements there, so it's definitely not an 1-to-1. So F is not a bijection. I got it. But here, if you need to now have F bar is a bijection. Now, what classes does it bring from
so
n?
Class of 1 and the class of 2.
You make class of 1 and class of 2 here. Let's say class of 1 and class of 1 and 0, I say. That would be better.
Okay, sir. Yes, sir.
Okay, then how does the map goes?
Then it goes to 0 and 1.
So here you said that, what is your sigma relation?
Sir, identity relation.
Okay, that is 0, 0 or 1, 1, right?
Yes, sir.
So it goes to 0, 0, it goes to 1, 1. No, rather the opposite here. Opposite would be better. It goes to 1, 1, goes to 0, 0. Everybody agreed?
are 1, 1 or only one?
Which one? Yeah, since we are talking about if you are talking about equivalence class, let's say we call it B, we call it A, and let's say A and B. Okay.
The opposite.
Yeah. Yes, your intent and example is absolutely correct to make it false. I mean, for those who are still wondering, I mean, I will give you a very simple example from this. Instead of n, infinite things, I will make it finite. So let's say ABC. What your friend is doing, your friend is trying to make this not 1-to-1. I will also try to make this not 1-to-1. What I will do is, so my B is, let's say my B is 2 elements, 1, 2. So what I will do, my FA will be equal to FB will be equal to 1 and FC will be equal to 2. So this prevents from making function F as 1-to-1. So F is not bijective. That's for sure. Now the row, I will define the relation row so that I can make a class of A and B and make a class of C separately. So I will make a class of A and B equivalence class. So I have to prove the symmetry and all this part like this and just keep CC. Okay. So what it will do, it will make that if you have A with respect to row, there will be 2 class. One class there will be either A or B. This is the same class, and another class will be C. Agreed? Now in sigma, what I will do in sigma, this relation, I just do it 1, 1 and 2. Meaning that with respect to B sigma, the classes are only 1 and 2. Now I will map this directly to, let's say, 1 and this directly to 2 with my F bar function. So F bar of A or B anything maps to one class. The same thing your friend has done. With an infinite set, I gave a simple example so that. Right now, F bar is a bijective function, 1-to-1, on-to both, but I have shown that F is not bijective. Clear? Yes or no? Happy, everybody?
Yes, sir.
Okay. So here, see, we plan to construct an well ordering of the pairs from natural numbers. Now, well ordering means, so what we do, first we need to prove partial order, whether it holds. Then it holds, we need to prove total order. So you know how to prove partial order, right? Reflexive, antisymmetric, transitive. How to prove total order? You need to take any 2 elements A and B. And you need to show either A has a relation with B or B has a relation with A. For any 2 elements. Any 2. Then it's qualified for a total order. Then when you have proven that something is a total order, then you have to prove it as a well order, meaning that it has a minimum element. Meaning that it has a minimum element. Okay, so gradually we will go and showing all these things. So minimum means, I mean, I would rather say minimum is an understatement. So minimum for every subset of elements. So we will explore this. So first, tell relation, is it a partial order? Tell me, first one, is it a partial order at all? So this way you have to go, huh? First you have to show this, second you have to show this, third you have to prove this. So if partial order fails, everything falls down. So is rho a partial order?
No, sir.
Which one fails? Symmetry, transitive. Antisymmetry fails, right?
1, 2 and 2, 1.
Correct. 1, 2 is related to 2, 1. Why? Because this or this. So 1 less than equal to 2. So it qualifies. Similarly, 2, 1 also qualifies because the B part less than D part, or any one true is done. So this is also happens, this also happens, but 1, 2 is not equal to 2, 1. So antisymmetry fails. So A is not partial order. Done. We did not have to go till well ordering. If it is not a partial order, it cannot be. Second one, if I have only changed this instead of or, what do you feel? Partial order, yes or no?
Yes, sir.
Everybody check the partial order thing.
Yes,
Good.
sir, it's a partial order.
Total order, yes or no?
No, sir.
Why? Just check. Is there for every element A, B either A related to B or B related to A?
No, sir. 1, 20.
No, sir. Yes.
Yes. Let's take these two elements. These are not comparable at all, right? So these two elements are not related. So you cannot build a chain of all the elements, right? These two elements are not related at all. So it's not a total order. Well ordering to chhodi do. Let us move on. You just complete this one. I am not doing it for you. Reflexive, symmetric, transitive. Complete this one. Next. I define a relation less than equal to L, and I say that either first component is less than C, or if first component is equal to C, I have second component less than equal to C. First of all, prove that this is a partial order. Do it yourself. Prove reflexive, symmetric, transitive. Okay, can you can do it, right? Antisymmetric, sorry. Antisymmetric. The previous slide also is antisymmetric. Everybody okay with this?
Yes, sir.
Yes, sir.
Reflexive, antisymmetric, transitive. Okay, by the way, just a little bit word of caution. Antisymmetric is not symmetric. Okay, do not say antisymmetric means not symmetric. Antisymmetric is a different notion, not symmetry is a different notion. I hope you understand that, right? Not symmetric is arrow A. This is symmetry. Sorry, arrow A dash is A dash row A. This is symmetry. Not symmetry is when this does not happen. Antisymmetry is arrow A dash and A dash row A implies A equal to A dash. So not of this and this are not related. Agreed, right?
Yes, sir.
Yeah,
Yes,
just
sir.
remember this one. This is a very critical concept. Okay, is it a total order? Go ahead.
Yes, sir.
So partial order, yes. Total order, yes. How can you prove? Now you have to prove now if it is yes. So take any ABCD, AB pair and CD pair. So what can happen with A and C? See, either A can be less than C, A can be greater than C, A can be equal to C. Okay, these three can happen. If A less than C, due to first condition, this relation holds. If A greater than C, again due to first condition, this relation will hold. I mean, the opposite way it will hold. So this CD. So here in the first case, your AB is related to CD. In this case, your CD is related in this manner to AB. What if A equal to C holds? Then we have to consider again two conditions. One is B less than D. One is D less than equal to B. If B less than D, or let's say less than equal to, I make it this way and put it, same thing, no problem. If B less than equal to D, then already we know that AB, CD. If D greater than, if B greater than D, so then the opposite thing will happen, A equal to C and the B greater than D. So then CD will be related to AB. So in either way, these two arbitrary elements are related to each other. So it's a total order. Clear how to prove? Now, is it a well order? Is it a well order?
No, sir.
Why?
One element can be related to many others.
No, that is not the case. Well order means take any subset, you have a minimal element. It's end to end. Take any subset. Let's say S is a subset. S is a non-empty subset. I mean, obviously this is non-empty, we assume. S is a non-empty subset of it. Okay. Now I have to prove that it has a minimum element. How can I prove? Suppose let us construct a set like this. This set contains of the natural numbers such that A, comma B belongs to A for some B belongs to N. Okay, so this set has a minimum. If S is a subset of A, this set, so for that subset of elements, if I just cluster all the A's together, this will definitely have a minimum. Let's say small x is the minimum element. Agreed or not? This will have a minimum element.
Yes.
Right? Now let's say small x is that element from or of this arbitrary set x. Now for this, what I will do, I will try to produce another set Y where B is N such that X comma B belongs to S. Now this set will also have must have to be some Y as a minimum element. This Y set has also have to be some Y as a minimum element. Right?
Yes, sir.
So therefore now consider the pair XY. So XY is the minimum of S. Okay?
Yes, sir.
This way. I just wanted to make sure that you prove it in this way, the total orders. Okay, so this is important, how you go to prove this. An infinite subset of A may contain a maximum element. Is this true or false?
Yes, sir. True, sir. True.
Yeah, I think it's trivial, right? You can just make it just think of it. I'm not going into it due to lack of time. I just complete one thing which is a different one, and then the rest which I have I will upload in the tutorial. But what we have is the similar one as we have done, well ordering and all this. Okay, see this one. Let me complete this quickly. Give an example of a poset such that S has a lower bounds, but greatest lower bound doesn't exist. Okay, let me give you a good example. Due to lack of time, I'm just giving. If you think also, you can make set of rational numbers with less than equal to relation. This is a POSET standard, right? Yes or no? This is a POSET. Set of rational numbers with less than equal to is a POSET. Agreed, na?
Yes, sir.
Yes, now let's take a set S, which is a subset of this rational number, a set of elements. I consider this subset as this one, x square greater than. Now, every rational number less than √2 is a lower bound of S, yes or no? I claim that every rational number less than √2 is lower bound on S. Yes or no? I claim this one.
Yes, sir.
Now, √2 is irrational. √2 is irrational. Right? √2 is irrational. So greatest lower bound of S does not exist because √2 is irrational. It's a set of rational numbers only. Okay, can you visualize now?
Yes, sir.
There could be many other examples. You can also take the set of irrational numbers, let's say something between 1 to 5, 6 or something. All irrational numbers between 1 to 5, all irrational numbers. And then you could consider a set between where the number belongs to, let's say, 0 or no, we can have 1 to 3 or 2. Let's say 2 to 3. All sets of 2 to 3. This will also do. Just try to see. This will also be with respect to less than equal to relation. Okay, there could be many. Just trying to show you that if also they have lower bounds in A, but we do not have greatest lower bound. Okay, with the lack of time, I have the similar kind of a problem where you need to show partial ordering, well ordering. You can do it, I guess. Okay, I have the same thing. I mean equivalence relation, equivalence classes, and another problem. I will upload it, but I request you to first go with yourself and then see the solutions. Okay, these are the things I have: total orders, partial orders, and all. Okay, so we will upload the solutions with the tutorial, but you please go on doing it. ठीक है? Okay, so we will meet again in the test day. All the best for your test.
Sir, excuse me, sir.
Yes, please.
Sir, can you please provide the test marks of the previous test before the next?
We will provide in a day. We will provide in a day. We are done. We just compile it. We will just mail it. I mean, we are done. We will provide in a day.
Thank you, sir.
Sure. We will provide in a day with the test and your mistakes with the comments. Okay.
Okay, sir.
Sure. We are a little late, but we are done. We have completed it. Okay. All the best. Let me stop the record.
Thank you, sir.